Welcome back to the deep dive. Today we are tackling what is arguably the most information-dense piece of art in all of chemistry, the periodic table.
It really is. It's an absolute triumph of logic. Most people just see this, a grid of letters and numbers.
Hmm.
But our source material, this fantastic exam survival kit you shared, it shows us that the table is actually a predictive map.
A predictive map, I like
Yeah,
that.
it's not just telling us what exists, it's telling us how everything behaves.
Exactly. And our mission for you, the learner, is to get past just, memorizing the layout. We want you to really understand the architecture, the logic behind the placement of every single element.
hmm
By the end of this, you won't see a chart. You'll see a shortcut to understanding chemistry.
And we can actually boil down the entire logic system to one sentence. It's something the source material says you must know by heart.
Okay, what is it?
The periodic table is arranged so that elements with the same number of outer shell electrons are in the same group. And critically, they share similar chemical properties. That arrangement right there is the ultimate aha moment.
So we're going to use this source material to first understand the logic of the structure atomic number first. Then we'll figure out why that outer electron shell is, well, the undisputed boss of chemical behavior.
And finally, how to apply that knowledge to build perfect explanations for any examiner.
Right.
So let's start with the foundation. The key areas examiners check are pretty straightforward. They want to know how elements are ordered, how you define groups and periods, and the absolute link between electron arrangement and behavior.
Okay, let's nail down that core structure. There's one massive misconception we need to clear up right away. Elements are not sorted by mass anymore. That old model had problems.
Huge problems. The modern arrangement principle is much more fundamental. Elements are arranged in order of increasing atomic number, period.
Which means increasing the number of protons in the nucleus.
Exactly. That number is the unique fingerprint for every single element. And the whole layout is structured by two key coordinates, sort of like latitude and longitude on a map. Groups and periods.
Let's start with the vertical columns, the groups. What defines an element's group number?
This is probably the most important link to make. Elements in the same group have the exact same number of electrons in their outer shell. So if you look at group 2, every single element in that column has 2 outer electrons. That's the rule.
And if they share that crucial outer electron count, what's the non-negotiable chemical implication of that?
It means they have similar chemical properties. They will react in fundamentally similar ways.
Oh.
So knowing the behavior of just one element in a group gives you this predictive template for the entire column. You don't need to test every single halogen. The whole group behaves similarly because they all have 7 outer shell electrons.
Okay, that covers the columns. Now for the horizontal, the periods. If groups are about outer electrons, what defines a period?
Simple. Elements in the same period have the same number of electron shells in total.
The same number of layers, basically.
Exactly. Period 1 elements have 1 shell, period 2 elements have 2, period 3 elements have 3, and so on. As you move down the table, you're just stacking another electron layer onto the atoms.
Okay, here's where I think the confusion can set in. If we take period 3, for example, from sodium all the way over to argon, they all have 3 electron shells.
Huh?
But their properties change so dramatically. Sodium is a fiercely reactive metal. Argon is a completely inert gas.
Right.
So why is there such a strong, gradual change horizontally when the number of shells stays the same?
That's an excellent point, and it's where the source gives us a really critical insight. As you move across the period, 2 things are increasing at the same time. The number of electrons, obviously, and the number of protons in the nucleus.
So the positive charge is getting stronger in the middle.
Precisely. But, and this is the key, all the new electrons are being added to the same outer shell. Because that positive nuclear charge is increasing, it pulls those outer electrons in tighter and tighter.
So it's like stretching a rubber band. The size of the atom actually shrinks as you go across, and the nucleus has a much firmer grip on those outer electrons.
Yes. That increasing pull changes the atom's chemical personality entirely. It makes it harder to lose electrons, and eventually, on the right side of the table, easier to gain them.
And that explains why you go from strong metals on the left to nonmetals on the right, all within the same shell structure.
That's the mechanism of gradual property change across the table.
That structural map is essential, but now we need to transition to the why. Why is that outer shell, that final layer, so incredibly dominant? Why is it the king of chemistry?
Okay, let's unpack this. Our sources call the periodic table a map of electrons, but I think we should think of it as a a map of chemical desire.
Desire.
Every atom wants to achieve stability. Usually that means getting a full outer shell of electrons, which is often called an octet.
And the number of electrons in that outer shell dictates how desperately and aggressively the atom pursues that stability.
Yeah.
It's really the only layer that interacts with the outside world, isn't it?
It's everything. That outer shell number dictates three critical things. First, the fundamental reactivity of the element. Second, its chosen method for achieving stability. So, whether it tends to lose, gain, or share electrons. And third, which type of bonding it's going to form.
So the table isn't just descriptive, it's a predictive tool. It tells you exactly what kind of relationship an element is looking for. It's like a chemical dating service where the address tells you everything about the participant.
That's a great analogy. Let's look at the real-world consequences, the aha moment. Take group 1, the alkali metals. They are all defined by having one lonely electron in their outer shell.
Right. And to get a full shell, they've got two options. Either gain 7 electrons, which is impossible, energetically speaking.
Impossible.
Or just lose that 1 electron.
And losing one is the path of least resistance. Therefore, they are all characterized as being always highly active, always reactive. They are desperate to shed that single electron to reveal a stable, full inner shell underneath. That desire is powerful.
Okay, now let's jump all the way across to group 17, the halogens. Fluorine, chlorine, bromine. They have 7 outer shell electrons.
So they are on the exact opposite side of the spectrum of desire. They just need one more electron to complete their shell.
They're so close.
So close. This means they always strive aggressively to accept an electron. That tendency, which is hardwired by their electron arrangement, explains why they are such effective, strong oxidizers.
So group 1 elements are electron donors, and group 17 elements are electron receivers. And this simple difference in their outer shell count drives the vast majority of basic ionic chemistry.
Absolutely. And you can see the pattern. The further you are from a full shell, generally, the less reactive you become until you hit the middle. But for the main groups, the pattern is absolute. The closer you are to a full shell, either by losing one or gaining one, the higher your reactivity.
And if we connect this to the bigger picture for the learner, this isn't just theory. This knowledge links the periodic table directly to understanding concepts like ionic bonding and covalent bonding. That group 1 element wants to lose an electron, the group 17 element wants to gain one. They are a perfect match for forming an ionic bond.
Exactly. If you understand the electron arrangement, you understand the motivation for all chemical reactions.
Which brings us to our third section. Applying this knowledge. Our source highlights that examiners are looking for much more than just definitions. They want you to construct a logical chain of explanation. This is where you score those higher marks.
Absolutely. When an examiner asks why elements in a specific group have similar properties, just saying they have similar behavior gets you 0 marks.
Right, that's just repeating the question.
You need to deliver the full explanation chain. You have to link location to electrons to behavior. This logic is what elevates your answer and can earn you, 2 to 4 marks right away.
Okay, let's walk through it. Imagine the question is, explain why lithium and potassium react similarly with water. We need to be crystal clear on the 3 essential links. What is the first one?
You start with location. The group number connects directly to the number of outer shell electrons. You must state that lithium and potassium are both in group 1, which means they both have 1 electron in their outer shell. That's link 1.
Okay, link 2 explains the consequence of that number.
That specific arrangement, 1 outer shell electron, dictates the chemical behavior. The atoms are unstable and have a strong tendency to lose that single electron to achieve a full stable shell. That's link 2.
And the final link, the conclusion, brings it all back to the question.
Exactly, because they have similar electron arrangements. 1 outer electron, and therefore the same chemical desire, to lose that electron, they necessarily lead to similar chemical properties. So they react in a predictable, similar way. You have to use that precise sequence. Location to electron count to behavioral tendency to similar properties.
That sequence provides a complete and unassailable answer. It shows you understand the underlying mechanism, not just the fact.
Correct. And this applies beyond just groups. It helps predict bonding. If they lose electrons, like groups 1 and 2, they're generally metals, and they favor ionic bonding. If they gain or share electrons, groups 4 through 7, they're generally non-metals. They favor covalent bonding with each other or ionic bonding with metals.
It's all integrated. The table really is a holistic map of chemical possibility.
And let's pause here for a second and give the learner the language checklist. This is the true survival kit advice from the source. The language you use matters tremendously.
Okay. When you are building your explanations, focus on using precise terminology. Use specific words like atomic number, group, period, outer shell electrons, and, crucially, electron arrangement. These words signal precision and mastery to an examiner.
And conversely, you have to eliminate the common mistakes. Avoid vague phrasing like, they behave the same. It's meaningless. Instead say, they have similar tendencies to lose electrons. Be specific.
And another critical error to avoid, which we mentioned earlier, but it's worth repeating, never say elements are grouped by mass. And don't mix up the definitions. Group is about outer electrons. Period is about the number of shells.
One common trick the source hints at is asking about the exceptions, like the noble gases in group 18. While they're in a group, their chemical behavior, or really lack thereof, is an extreme example of the rule. They already have a full outer shell, they have no chemical desire at all. That stability is the entire point.
Right, understanding those boundary conditions actually reinforces the rule. If the goal is stability, then the elements that have already achieved it prove the point. Okay, time for our final synthesis. Let's run through the quick self-check our sources provided for you. If you can walk into your exam confident in these 3 facts, you've mastered the logic.
1. Group means the same number of outer shell electrons. 2. Period means the same number of electron shells. And 3. The table is ordered by increasing atomic number.
That's the elegant logic. It's not a random poster of elements, it's a map. Your location tells you your electron address, and that address dictates your entire chemical identity. Once you see the electrons, you see the desire.
And what's fascinating is how neatly this map organizes those competing desires, the tendency to lose electrons versus the tendency to gain or share, since these tendencies fundamentally define the difference between elements that favor ionic compounds and those that favor covalent compounds.
So here is the provocative thought for you to chew on. If the periodic table is a map of these chemical tendencies, where exactly would you expect the natural boundary, that critical dividing line between metals, the electron losers, and nonmetals, the electron gainers and sharers? Where would you expect that line to be? Think about the elements that sit right on that threshold and what their address suggests about their ambivalence.
Reflect on the location of the metalloids, and you'll start to see the chemical compromises that make the transition from ionic to covalent possible.
That's a deep dive. We'll catch you next time.